Can one of you tell me what a telescope is used for?
Is for looking at stars.
Only stars.
No, planets and other stuff.
Okay. Basically to look at distant objects. Fine. The telescopes that you have in mind are very powerful telescopes which help you observe other planets in detail. Okay, fine. But we are going to discuss at this level about a basic telescope, which is more like a binoculars, you can say. Okay. Of course, it can be used to look at stars or planets, whatever you want, but it won't be able to show them in that much detail or that much magnification. Okay, fine. So in a telescope also, or when you see through a telescope also, what we want is angular magnification of the object. When we look at the object directly, it appears tiny, very tiny. Actually, see, suppose you want to look at a building which is very far away from you, maybe 1 kilometer away or something, or very far also you can visualize, nothing wrong in that. Let's say you want to look at an aeroplane which is flying in the sky. Uh, when you see it directly, it appears very small to you. Fine. What we want is a zoomed image. We want an image which subtends a bigger angle on our eye than the object itself. Okay. Same as how we wanted in a microscope. Okay. So suppose there's an object placed at some distance in front of the eye. You know that the ends of the object subtend a certain angle on your eye. Okay. The lower end and the upper end, if you connect them to a single point on your eye, they subtend a certain angle. Fine. Now, this same object, if it is taken farther from you, somewhere here, and now you draw lines connecting the upper end and the lower end to your eye. The line connecting the lower end to your eye is the principal axis itself, as you can see. If you draw a line connecting the upper end, you get a line like this. And clearly, it now subtends a much smaller angle on your eye. Fine. So the same object, when it goes farther from you, it subtends smaller and smaller angles. That is why it appears smaller to us. The object size won't decrease, no. It's the same sized object placed at a different distance and it appears smaller to us. So just like in case of microscope, in a telescope also, what we want is angular magnification. What we are looking for is angular magnification. Okay. So basically, for this far away object, okay, which subtends a very small angle on our eye when seen directly, we want to form an image, okay, which subtends. For example, let's say this is the image formed by the object. Okay, we would like to form an image which subtends a bigger angle on our eye. That is what we aim to do by using a telescope. Okay, same thing is what I mean. We did the same thing in case of microscope also. But the only difference between a telescope and a microscope is, in case of microscope, the object will be very close to the lens. For a simple microscope, in fact, it has to be within the focal length. Okay, we had discussed this in detail. And for compound microscope, it has to be between f and 2f from the first lens. So it should be close to the microscope. Then you can get that angular magnification. Now, telescope, the basic purpose itself is to look at faraway objects, right? So you can't expect the object to be close to the lens. It will be far away from the lens, but you need a magnified image. Okay. At least angular magnification is what we are looking for. So let's see how this can be done. Now, since the object is far away from the observer, we'll assume u tends to infinity. See, in real life, we can't literally see anything which is at infinite distance from us. All the things that we see around us are at finite distance only. But you are going to substitute these formulas in the lens, you are going to substitute these distances in the lens formula, right? Imagine applying the lens formula. 1 by v minus 1 by u is equal to 1 by f. Now we want the image to form quite close, maybe at the near point distance or slightly away from it. So image distance will be close, approximately 25 centimeters. Suppose you want the image to form at the near point distance. Then image distance is 25 centimeters. But where is the object? Kilometers. Okay. Even if it is meters compared to centimeters, there's a factor of 100. One meter is 100 centimeters. Okay. So even if the object is some meters away or kilometers away, then u will be a very large number. Okay. And focal length of the lens will be in centimeters only again. Okay. So f is approximately a few centimeters, maybe 10, 20, something like that. So compared to v and f, u is very large. So in this equation, it won't make much difference if you substitute 1 kilometer or infinity. The answer for image distance will almost be the same, or the answer for magnification will almost be the same. Okay. So even though we are looking at something which is not at infinite distance, while substituting in the lens formula, you can assume u tends to infinity when dealing with a telescope. Is this point clear? Isha and Rishi, did you understand?
Yes, sir.
Okay. Now, what we are looking for is angular magnification. Now we have two choices: convex lens, concave lens, or you can say, I can say converging lens and a diverging lens. Now a diverging lens, we know the image formation by a diverging lens. Diverging means focal length is negative. If focal length is negative, image will always be smaller than the object, and you cannot expect angular magnification from it. Okay. So in a telescope also, just like in a microscope, you cannot use diverging lenses or concave lenses. Fine, because it is going to form an image which is smaller than the object, which is not of any help to us. It won't subtend a greater angle on our eye. So we are left with only one choice. We need to use a converging lens, which is a convex lens. Okay. Now one of you tell me, if object distance tends to infinity, where does the lens form the image?
Focus.
Focus, correct. So, okay, we'll consider the lenses one by one. Let's say this is one lens whose focal length is f1. Okay, you can assume the focus to be somewhere here. Object is on the left side. If object is on the left side, rays will be incident this way. And if rays are incident this way, this side is positive for this lens and the other side is negative. Okay, and focal length is positive for a converging lens. Focal length is positive. So you have to take the focus which is on the positive side. Fine. If object is at infinity, image has to form at the focus. That's fine. But how do we do ray tracing for an image which forms at the focus? As usual, suppose there's an object somewhere here. We take two rays from the tip of the object, right? We take one ray like this. Okay, understand this carefully because the diagram given in your textbook is not very informative, you can say. You may get confused, like how can we draw it like that? If this object is at finite distance, it's not at infinity. I'm doing the basic ray diagram. One ray passes through the focus after refraction, and another ray passes through the optical center. It does not undergo any deviation, goes straight like this. You get the image somewhere here. Okay. As object tends to infinity, image tends to focus. But how can we draw the ray diagram for such an object? Like, see, you'll again take two rays. That's fine. One ray will be taken parallel to principal axis. It will pass through the focus. This second ray that is there, okay, from the object to the lens, which passes through the principal axis. If object tends to infinity, no, this ray will become almost parallel to the principal axis like this. Okay. In fact, if the object is at infinity, very, very far away, that ray will be striking the lens like this. You won't even be able to notice you won't even be able to notice the image there. Okay. So And you are not supposed to notice the image also, because the magnification produced by a lens is V divided by U. If object distance tends to infinity, then magnification becomes 0. Okay. If magnification tends to 0, what is the basic definition of magnification? Height of image divided by height of object. Then if magnification tends to 0, height of image tends to 0. Then how will we write any equations? How will we derive anything? Cannot be done. Okay. So for image formation of a very far away object, this is not the ray diagram that we take. If the object is of small size, no, like this, like the object that you see on your screen, its image height will be 0 or tending to 0. If object goes very far away, image tends to focus. And because object distance is tending to infinity, or it's a very large value, magnification will be tending to 0. You won't be able to notice the image at all. Okay. So for small objects which are far away, telescope is not useful. You won't be able to see the image. Okay. Suppose the object is very large, then it can be seen. Okay. Now see, when we do ray tracing, till now, all the cases that we considered, whether it's mirrors or spherical surface or lens, we always took an object which is smaller than the lens. Okay, I don't know if you have noticed that or not. We never considered objects which are bigger than the lens itself. But in case of telescope, that is what is going to be considered. Like suppose you want to look at an aeroplane or a building or a person who is far away. Let's say you are using a binoculars to watch a cricket match or something. You'd like to see the players. Okay. So if you consider the player or aeroplane as an object, they are definitely bigger than the lens that you are using. Okay. So in case of telescope, this is what you have to keep in mind. The object is bigger than the lens. Okay. And let me show you a picture, let me help you visualize how the ray tracing is done in that case. So we'll assume a diagram, or we'll consider a diagram which is like drawn to scale, maybe almost like drawn to scale. So suppose this is the lens. It has a positive focal length and object is very far away from the lens. Okay. Now the focus of the lens will be somewhere here. Assume this is the object. Okay. You must consider an object which is significantly bigger than the lens. If it's a small object, you won't, like, the image size will be tending to 0. You won't be able to see it. We have discussed that already. Now for this kind of object, how to do ray tracing? We never did that. Now if you take a ray parallel to principal axis, okay, it won't even pass through the lens. That ray is useless for ray diagram. Okay. So in case of a telescope or in case of far away object like this, what we do is we do take one ray parallel, or one ray straight towards the optical center. This one. Okay. And it will pass without any deviation, and we know it. How do we take another ray? Take it to anywhere on the lens. Okay, just ensure it is close to the principal axis. The point where it strikes the lens is close to the principal axis. We take it like this. And as object tends to infinity, image tends to form at the focus. So we know where the focus is. This object as such is not at infinity. It's at a finite distance, but a large finite distance. So image should form at very close to the focus, somewhere here. So the ray bends like this. It won't pass through the focus. This is not a ray parallel to principal axis. It won't pass through the focus. It will miss the focus, and you will get a small image here. You may not even be able to notice it actually. The image forms here. Fine. I'll just take a picture of that image and zoom it in. Just a moment. Yeah, so that image formation part, if you zoom in, you'll be able to observe the very, very small image that is formed. So this thing that you see here is the image. That is where the refracted rays are meeting. Okay. But observe the incident rays. One of you tell me, how much is the angle between the incident rays? Is it large or is it very small?
Very small, sir.
Very small, obviously. And if the object actually tends to infinity, if the object distance actually tends to infinity, this angle tends to 0. As you take the object farther and farther from the lens, the angle will become smaller and smaller. Okay. So the ray tracing in case of image formation by the first lens of a telescope is done like this. Suppose this is the lens and we have to visualize, or we have to consider the principal axis first. Assume this is the focus, primary focus. Rays are incident from the left side. Now you can see the rays that are incident are almost parallel to each other, not the principal axis. The rays are parallel to each other. Okay. One of those rays passes through the optical center. So this point. Assume object is actually at infinity or very far away, then the other ray should be parallel to this one. Okay. Angle tending to 0, almost equal to 0. So the second ray will be incident like this. Okay. And after it strikes the lens, how should it bend? It should bend as if it is forming an image at the focus, because if object is at infinity, image must be at the focus, right? Now let's mark that focal length distance. It's still here. The image should be formed on that line. So this ray bends like this to meet the other ray exactly at a distance equal to the focal length. And this is where you get the image. Okay, you can call this height as h1. That's the image formed by this lens. Okay, so this very small image itself is what I have shown now. You are seeing an enlarged view. Okay, so if object is at infinity, from the upper tip of the object, if you consider two rays, those two rays will be parallel to each other. And they bend like this. This is the diagram that you see in your textbook also, or in most standard books, this is what you see. Okay, but actually, this is where it comes from. Okay, this diagram itself changes to that diagram. So remember, in case of a telescope, we are dealing with objects which are bigger than the lens, which we have never done till now. Okay, that's why the ray diagram will be slightly different. Okay. Again, this picture is important actually. Thinking, I mean, visualizing it this way is important. Now see, this is the actual object, right? The actual object, the upper tip of the actual object is subtending a certain angle on the lens. We'll call this as theta naught. In place of the lens, had your eye been here, okay, suppose you are trying to look at it directly, whether it's an aeroplane or a player playing a cricket match or whatever it is. Suppose you try to look at them directly, your eye will be here at this distance, and that angle theta naught, is what the object subtends on your eye. Okay, so when the object is viewed directly, the angle it subtends on your eye is theta naught. Angle subtended when object is viewed directly. Okay. Now what we want is, we want the telescope to enlarge this angle. We want angular magnification. Okay, let's see how that can be done. So first we allowed those rays to pass through a converging lens. This lens, this is the first lens. It has a positive focal length and it forms an image at its focus. Now what we will do is, we will enlarge this image further such that the rays finally subtend a large angle on our eye. That is what we are going to do. And how do we enlarge this image further? We use another convex lens, another converging lens. Okay. Let's see what happens to this image now. the image formed by the first lens becomes an object for the second lens. So that is how we are going to consider it. So I'll move all this to the left side. The rays are coming from infinity, so they'll be parallel to each other. Okay. So you can call this image as I1, image formed by the first lens. This is an object for the second lens now. So, and we want an enlarged image, no? So what we will do with the second lens is same as what we did in case of microscopes, simple microscope or compound microscope. See, in microscope also, the first lens formed an image. The second lens enlarges that image, right? The same thing is going to be done in a telescope as well. Okay. So consider another lens here. Distances and all are very important. We'll do the calculations later. First, understand the ray diagram. So consider another lens here. And we want this lens to form an enlarged image. And we want image on the left side itself, not on the right side. Why? Because we are going to keep our eye on the right side here. For us to be able to see an image, the image should be at least 25 centimeters from our eye. Okay, so it has to form on the left side only, not on the right side. If image forms on the right side, the problem is like the second lens, if it forms an image somewhere here, then the problem is you'll have to keep your eye at a further distance of 25 centimeters from it and look. So you will have to hold the telescope very far away from you. That will be uncomfortable. And that's not what we want. Okay. So the final image should form on the left side of the second lens. Second lens, let's say its focal length is f2. Obviously, that is also positive. We are using converging lenses only. Okay. Now the image formed by the first lens behaves as an object for the second lens. So I'll cut off these rays. Now if you treat H1, the image of height H1, as an object for the second lens, basic ray tracing, we want the image on the left side. For image to be on the left side, this first image that forms should be at a distance d from the second lens, where d is less than its focal length. Okay, like I'll show you the ray diagram in case of a simple microscope. Yeah, this one. If object is within the focal length, then you can get an enlarged image on the same side. That is what we are looking for. So the first image that forms should fall within the focal length of the second lens. Okay. Just a moment. This I'll have to show this in blue itself. This is the focal length of the second lens. F2. H1 has to lie within that distance F2. Okay. Now if we do the ray tracing, if that distance is F2, then you will have to visualize a focus on this side as well. Now this image H1 that we got is a small image only. It's not as big as the object. This image is smaller than the lens. So we can do basic ray tracing now, as we always did. We take one ray parallel to principal axis. What happens? It will pass through the focus after refraction. And another ray directly to the optical center, passes without any deviation. Now these two rays, as you can see, they're not going to meet after refraction. Okay. On the right side, they will not meet because they are going away from each other. Then they will appear to be coming from a common point on the left side. And that common point, okay, is here. So finally, what the observer sees is this image. Okay, you can call this as I2. Okay, I1 is the first image, I2 is the final image. So if you have your eye on the right side, the rays will appear to enter into your eye from I2. Okay, so that is what the observer will finally see. So this is what happens when you see through a binoculars or something. But yeah, some of you might be having this doubt. When we see through a binoculars, we see an upright image. Why are we getting an inverted image here? We'll get to that point. Okay, but see, how did we achieve magnification here? When the object was viewed directly, okay, when you look at the object directly, it subtends a very small angle on your eye because the object is far away. Whether it's an aeroplane or a building or a person, whatever it is, it's a small angle, theta naught. It subtends the same angle on the first lens also. So you can visualize that angle here, theta naught. But see how the rays are finally entering into the person's eye. They are entering at a much larger angle, theta, that you can see here. Okay, clearly this angle, the one I'm highlighting in violet, this angle is bigger than this angle, the one I am highlighting in green. That is the angular magnification achieved by using a telescope. And we need to derive an expression for it. Okay. What is the basic formula for angular magnification? Just a moment. Okay, I showed it in this diagram itself. Never mind. Let's copy this. 1 second. Rishi, can you tell the basic formula for angular magnification?
Sir, it's theta naught is equal to h by d, capital D.
Okay. First of all, that is not magnification. It's just the angle that you are telling me. And that angle, theta naught is equal to h by d, is the angle subtended when the object is kept at the near point distance and seen. Okay, that is valid in case of a microscope. When we see the object directly, the angle subtended on our eye is that much, because we can assume the object to be at the near point distance. But when using a telescope, the object is never going to come to your near point distance. It will be far away only. Okay, so this angle is irrelevant in case of a telescope. I'm just asking you the definition of angular magnification. I'm not asking you how much angle it's subtended.
Sir, is it 1 by d is equal to f plus x by x?
You are giving me the formulas. I'm asking what is the basic definition of angular magnification. Okay, it is the final angle subtended on our eye divided by the original angle subtended on our eye. This is what we call as angular magnification produced by an optical instrument, whether it's a microscope or a telescope. Okay, final angle divided by initial angle or the original angle. Okay, so now in this diagram, from this diagram, we need to derive this ratio, theta divided by theta naught. Okay, now see, for our clarity, we have shown significantly large angles here. The angles almost seem to be like 30 degrees, 45 degrees. Okay, but in actual case, they won't be that large. They'll be small angles only. Fine, but theta will be bigger than theta naught. Angular magnification will be produced, but the angles will be small, still small. So for small angles, tan theta is approximately equal to theta. We are going to use that. So theta by theta naught is same as tan theta divided by tan theta naught. Okay. Now let's use these triangles to get tan theta value and tan theta naught value. Again, I'll have to zoom in a part of this picture. Just a moment. Let's say from, okay, we'll consider from here to here. 1 second. Just to help you visualize with visualize tan theta properly. Okay. Okay, so this is that second image formation part that I have taken. Let's see the distances carefully. Okay, let me use different colors. Yellow. This yellow dot is the distance to this yellow dot is the focal length of the second lens, f2. Okay. Where did the first lens form the image? At its focus. Okay, because the original object was at infinity, first lens forms the image at its focus. For the first lens, I'll use green color. From here to here is the focal length of the first lens. Okay, f1. Right. Now what we want is tan theta divided by tan theta naught. You can see the angle theta naught on the extreme left. If that angle is theta naught, then this angle inside will also be theta naught itself. Okay. Now let's consider a triangle of which theta naught is a part. That will be this triangle, the one I'm highlighting in red. Rishi, do you agree with this or not?
Yes, sir.
Okay. Now this distance is the focal length of the first lens, that horizontal distance, one side. The opposite side is h1. So yeah, Isha, tell me how much is tan theta naught from this triangle?
So h by f1.
h1 by f1, correct. That is tan theta naught. We'll approximate it to theta naught itself. Okay, fine. Isha, you only tell me how much is tan theta? Can you express it or not? Theta is part of a right angle triangle like this, the blue one. How much is tan theta? Okay, just tell me this. Can you say it is h1 by f2?
Yes, sir.
F2 is up to that yellow dot, no? But that side of the
Okay.
triangle is not extending up to that distance.
Yes, sir. Yes. No.
Okay, so we cannot. So what we are going to do is we are going to call this distance as small d. So what is small d now? Small d is the object distance for the second lens. Okay. Now we can write tan theta as opposite side h1 divided by small d. And this is approximately equal to theta itself because they are actually small angles. Rishi, is this clear?
Yes, sir.
Okay. Therefore, the angular magnification produced by the telescope, by definition, it is theta by theta naught. If you use the values that you have derived now, it becomes h1 by small d divided by h1 by f1, focal length of the first lens. h1 gets cancelled. You will be left with f1 divided by small d. This is the formula for angular magnification produced by a telescope like this, which makes use of two lenses, where small d is the distance of the first image from the second lens. Okay, you can call it as object distance for the second lens. And Richard, a little while ago, when I asked you the formula for magnification, you told something in terms of d, f, and x. Can you repeat that?
The d is small. 1 by d is equal to f plus x by fx.
Okay, 1 by d is basically 1 by f plus 1 by x. Can you tell me what are d and x in this? F is focal length, obviously. What are d and x?
Sir, d is the it's the object.
Distance.
No,
Correct.
yeah,
It's the distance of the object, magnitude of distance without sign. And what is x?
x is the first image distance to no. Oh,
Okay,
it's the
okay, let it be. Generally, for image formation by a lens, in this case means when object is within the focal length, image forms on the same side like this. Okay. In this case, if you call object distance as object distance as d and image distance as x from the lens, then you substitute them in the lens formula. This is how they get related. So small d is the object distance from the lens and small x is the image distance from the lens, actual distances. Okay. Now we got magnification of telescope in terms of small d. This formula is useless basically. Why is this useless? Because nobody is going to tell you small d in the problem. They are going to tell you where they want the image to form. So let's go back to the ray diagram. Small d is the object distance, right, from the second lens. So in this diagram also you can visualize. Okay, why am I drawing to the focus? Okay, because first image formed at the focus of that first lens. Okay, so this is small d. Okay, and what is x? This is x. Where the final image forms is x. That is what they are going to give you in the problem. Depending on where the final image forms, you will have to, or you can adjust this distance. In a telescope, the lenses will be adjustable. You can move them forward and backward. So by adjusting that distance, you can get the image wherever you want. Okay, at whichever distance you want. And that object and distance and image distance are related this way. Okay, but this is by the second lens, right? So you'll have to write f2 here. Therefore, if you go to the magnification formula, angular magnification, it is f1 divided by d. I can take it as f1 into 1 by d. Basically, it becomes f1 into 1 by f2 plus 1 by x. This is the actual formula for magnification by a telescope. f1 is the focal length of the first lens. f2 is the focal length of the second lens. First lens, which is near the object, what is it called? Same names that we used in compound microscope. The lens closer to the object, what is it called? You have to remember these names because in problems they'll use those names. Okay. The lens closer to the object is called the objective lens. And the lens closer to the eye is called the eyepiece. Okay. They won't call it first lens, second lens. They'll call them objective and eyepiece. You need to understand. Objective is on the object side. Eyepiece is on the side of the eye. Okay. And focal length also, they'll write it as f0, fe instead of f1 and f2. So the formula for magnification ultimately becomes f1 is f0, f2 is fe plus 1 by x. X is the distance where you want the final image. Now that is your choice. You can make the final image form wherever you want. Some of them may like to see the distance at the image at the near point distance. Okay. So x, the distance where the final image forms, could be anywhere from near point distance, which is approximately 25 centimeters, to infinity. You can make the image form wherever you want. Okay. And based on that, the magnification will vary. Now in NCERT textbook, they have taken only one case of magnification. They assumed final image forms at infinity. Okay. If final image forms at infinity, then how much is the magnification you get from the telescope? It will be f0 into 1 by fe plus 1 by x, which tends to infinity. 1 by infinity tends to 0. Therefore, the magnification becomes f0 by fe. Okay. You want final image at infinity, means small d should become the focal length of the eyepiece. If object is at focus only, no image will form at infinity. Okay. So that is one case of image formation. Small d is not always equal to fe, focal length of the eyepiece. But in that case, you will get, if it is so, you will get image at infinity. And in that case, the magnification becomes f0 by fe. This is the formula that you see in your textbook for magnification of a telescope, by a telescope. Okay. And when this happens, When what happens? When final image forms at infinity. Okay. We call that setting as normal adjustment of a telescope. Okay. Why do we want the final image to form at infinity? Because for our eyes, it is very comfortable to look at something which is far away. Now you may ask, sir, object is also at infinity. Why form the image at infinity? Because it's an image which subtends a bigger angle on your eye than the original object. That's all. We want bigger angle. We want angular magnification. It doesn't matter where the image forms. And you are getting angular magnification, f0 by fe. All you need to do to get an enlarged view or a magnified view is ensure that f0 is greater than fe. That's all. If f0 is more than fe, magnification will be more than 1. That's what we want. Okay. So in a telescope, focal length of objective has to be greater than the focal length of eyepiece to get magnification. If it is smaller, you cannot get magnification. Okay. So is everything clear? Any doubts in this?
No, sir.
Fine. So for normal adjustment, means if you want the final image to form at infinity, small d should become equal to f2. Now first image is forming at f1 and small d becomes equal to f2, then the total distance between the lenses will be f1 plus f2. Okay, let's draw the ray diagram in that case also. I'll make use of this. We want final image to form at infinity. It's very important to know how the rays will be traveling in that case. Okay, in any case, actually, you should be able to draw the ray diagrams. Okay, we got image by the first lens. Till there, I'll keep as it is. The rest of the diagram will have to be changed. We now want the final image at infinity. For the final image to form at infinity, this first image that is formed should be at the focus of the eyepiece. Now, where is the first image forming? First image is forming at the focus of the objective. Let it be. This distance is f0. The other side distance should be fe, focal length of the eyepiece. Then the image forms at infinity. So let's draw the ray diagram in that case. Just putting the observer's eye aside for a while. So assume this distance is focal length of the eyepiece now. At the same distance on the other side, it will have another focus. So somewhere here. Okay. Now if you do ray tracing, this first image that is formed by the first lens behaves as an object for the second lens. So one ray parallel to principal axis passes through the focus after refraction. Another ray through the optical center passes without any deviation. This is what the ray diagram looks like. And you can see that the two rays emerging out of the lens are parallel rays. Means they tend to be coming from a common point at infinity. That is what we mean by final image forming at infinity. Okay, so in that case, the total distance between the two lenses will be f0 on one side, fe on the other side, f0 plus fe. In other cases, in case you don't want the final image at infinity, you want it at a nearby distance, then what is the total distance between the lenses? It is f1 or f0. Okay, first distance is f0. From here to here is the focal length of objective. First image has to form at focal length of objective because original object is at infinity. Now what is the total distance between the two lenses? It is f0 plus d, small d. Okay. Now, why am I concerned about, or why am I spending time on distance between the lenses? Because in case of telescope, there is a term called length of the telescope. It is defined as distance between the lenses. So generally, L is equal to focal length of objective plus the object distance for the second lens. Okay, so this is the basic formula for length. In case of normal adjustment, what is normal adjustment? Final image forming at infinity. Keep this point in mind because in problems they will use this term, normal adjustment. So you need to understand that it means image forming at infinity. Now in case of normal adjustment, the object distance from the second lens becomes its focal length. Therefore, the length of the telescope becomes f0 plus fe. So this is for any case. The second formula that we write here is for the case of normal adjustment. Okay. Let's solve one problem based on this. Okay. Take a screenshot of this ray diagram. You can refer to it if needed. Wait, I didn't mark F0 in this. Okay, F0 has been marked here. We'll mark F0 here also. Just a moment. F2, okay, let's keep F2 in yellow itself. From the second lens, I'm keeping it in yellow. F2 is actually FE. I'll write it as FE. Focal length of eyepiece. And the distance of image from the first lens is F0. This distance is F0. So you can observe all the distances in this diagram. Image distance, final image distance is X. The object distance from the second lens is D. Okay, take a screenshot of this. And see, now you can take screenshot, you can see and answer, all that is fine. But you should be able to draw this ray diagram on your own. Okay. Practice ray diagrams thoroughly. Now, the question is, see, obviously object is at infinity. Focal length of objective. Now see, in a telescope, we know f0 should be greater than fe. I'll give you a problem based on that itself. So focal length of objective, let's say, is 40 centimeters. And focal length of eyepiece, let it be some 10 centimeters. Object is at infinity, needless to say. If image forms at near point distance is 25 centimeters, no, so image should form beyond that only. So if image forms at 50 centimeters from the eyepiece, first thing, derive magnification, angular magnification only. We don't care about linear magnification in case of telescope and microscope. Derive magnification. Second thing, derive the length of the telescope. Solve this carefully. Right. How much did you say it is?
4.2, sir.
Okay. Tell me the formula for magnification produced by a telescope.
F0 into 1 by FC plus 1 by X.
1 by Fe plus 1 by X. F0 is focal length of objective, which is 40 centimeters. Fe is focal length of the eyepiece, which is 10. And where do you want the image to form? Image should form at 50 centimeters from the lens. That's all. 1 by 10, 1 by 50. 1 by 10 is like 5 by 50 plus 1 by 50, 6 by 50. So 40 into 6 divided by 50. 4 sixes is 24 divided by 5. The answer is 4.8 exactly. Okay, that's the magnification we get. Okay. And Rishi, can you derive the length of the telescope now? Have you noted the formula?
No, sir, can you show it once?
What is the meaning of length of telescope?
Sir,
It's
how
the
long it's from the eyepiece?
it's just the distance between the lenses. Okay, distance between objective lens and the eyepiece lens. Okay. And again, if you have the ray diagram in your mind, it's very easy to tell what is the basic expression for length of the telescope. It will be f naught plus this object distance d. So the length of the telescope is f naught plus d. Is it clear?
Yes, sir.
Now apply that in this case. What exactly is d?
The focal length, second length.
No, it doesn't look like that. No, in this diagram,
No, it's the first image to the second lens.
first distance from the first image to the second lens, that is nothing but object distance for the second lens, isn't it?
Yes, sir.
So small d is the object distance from the eyepiece. But in the problem that is not given to you. You have been given where the image should form. Okay, and you know how to link d and x. That formula you are comfortable. Use that. One by d is 1 by fe plus 1 by x. So d becomes x fe by x plus fe. That's all. Substitute it. Therefore, the length of the telescope in this case becomes f naught is 40 plus, we wanted the image to form at 50 centimeters. Fe is 10 divided by 50 plus 10, 60. 50 by 6 is 8.3 approximately. So 40 plus 8.3, 48.3. Okay, the answer is close to 48.3 centimeters. Okay.
Yes, sir.
So listen, if you just use two lenses, no, this is what happens. And ultimately what you see is an inverted image. Okay. This is what happens in an astronomical telescope. This is what actually happens in an astronomical telescope. Okay, a telescope that you used to see faraway objects like spots on the sun, planets and all. This is what happens. But in a binocular, when you see through a binoculars, you don't see inverted images. You see upright images, which are magnified. Okay. So that telescope is called a terrestrial telescope. Terrestrial means something that is on the land. Okay. On the earth. So if you want to look at some building, faraway building or faraway person or something, then you use something called a terrestrial telescope, which produces upright images finally. So how does it do that? It's a simple idea. We have to invert the image that is formed. Okay. But we don't invert the final image. This intermediate image that is there, we invert this before we do the final magnification. Okay. Now, how is that inverting and all done? Again, we'll have to go back to the cases of image formation by lenses. Okay. Just a moment. Consider a converging lens first, positive focal length. For a converging lens, the important points which help you in ray diagram, drawing the ray diagram, are the points at distances f and f on either side. That's a distance equal to the focal length. Okay. And you also need to consider points at distances 2f and 2f on either side. So if that distance from the optical center is f, then this will be 2f. Okay. Suppose object is beyond 2f on the left side. Okay, just a moment. Let me copy this. Suppose object is beyond 2f on the left side. Basic ray tracing only. These are small objects that we are dealing with. One ray parallel to the principal axis passes through the focus. Another ray straight to the optical center passes without any deviation. Object was beyond 2f, as you can observe. Look at where the image forms. Tell me, what is the region in which the image has formed? It has formed between f and 2f. Okay. This is one case of image formation by a converging lens. You get an inverted image, but it is diminished. So it won't serve any purpose in a telescope, this case. I mean, in magnification, it won't serve any purpose. Fine. Next case of image formation by a converging lens. We considered object beyond 2f. Now assume object is exactly at 2f from the lens. If object is exactly 2f at 2f, again, basic ray tracing. This ray passes through the focus on the other side after refraction. And another ray drawn through the optical center passes without any deviation. And you can see where the two rays meet. They will meet exactly at 2f on the other side. This is an interesting case actually. Object distance equal to image distance. So if object is at 2f on one side of a converging lens, image will also be at 2f on the other side of the converging lens. Okay. You get an inverted image which is of the same size as the object. And another case of inverted image formation. If object is between f and 2f on this side, say somewhere on this side, so you should do this exercise once on your own. Okay, not once, you should be able to do it any number of times. Like you have to practice it so that you can draw the ray diagrams very easily. Other ray will pass like this. And where are they meeting? They are meeting beyond 2f. So if object is between f and 2f, image forms beyond 2f. This is also an inverted image. On that side. Okay. The last case, when object is within the focal length, you get an upright image on the same side as the object that we have already discussed. Okay. Now, why are we discussing all this in the first place? We are trying to make the image formed by a telescope an upright image ultimately. We want the image on the same side as the object. Same side means same side above the principal axis is what we want. So for that purpose, what we do is, I'll have to use this diagram. Okay. Let me erase all the unnecessary things. Just a moment. The first image forms at the focus of the objective. Let it be. From there onwards, we'll be making some adjustments. We'll be making some changes. Okay, observer will introduce later. What we first want to do is, we want to invert this image. Okay, so we use a lens called a correcting lens. And what exactly does the correcting lens do? Let's say this is the correcting lens. It's also a converging lens itself. Assume its focal length is FC. Okay, we ensure that the correcting lens is at a distance of 2 times its focal length from the first image. First image forms at the focus of the first lens, no? F0. That is shown to you in the diagram also. First image forms at F0. Keep the correcting lens at a distance 2 times of FC from F0. So effectively what happens, this first image, which is now an object, okay, the first image is now an object for this lens, no, correcting lens. It's like the object is at 2 times the focal length. If object is at 2 times the focal length, image also forms at 2 times the focal length, and you get an inverted image. So what happens is, this correcting lens forms an inverted image here. What size will that inverted image be? We call this height as h1. This height will also be, h1 itself. Why? Because if object and image are formed at the same distance on either side, object height and image height are going to be the same. Rishi, is this clear?
Yes, sir.
And after this, what we do? We use the eyepiece. And as usual, we make it magnified. Okay, so correcting lens will come in between. It makes the first image upright. And then we use the eyepiece. Eyepiece will be placed quite close to this. And in this case, what will happen if you do further ray tracing? One ray parallel to principal axis passes like this, another ray passes like this. They are not going to meet on this side. They'll meet on the other side. This is where you get the final image. Okay, so the magnification after this is as usual. So you will have objective lens. Eyepiece lens will also be there. In between, you have an extra lens called the correcting lens. This kind of telescope is called a terrestrial telescope. Binoculars. Okay, so that the final image that you see is an upright image. I'm not drawing the complete ray diagram, but did you understand what happens or not?
Yes, sir, understood.
Okay. And by putting the correcting lens this way, okay, by ensuring that it's at a distance 2 times of FC, and this image also forms at the same distance 2 times of FC, we won't be disturbing the magnification, because this image and this image are of the same size. And after that, what the eyepiece does is the same as what it was doing before in terms of magnification. So the overall magnification of the telescope won't be disturbed. Okay, so the magnification of the telescope, whether it is astronomical or terrestrial, it's always given by this formula, f0 into 1 by fe plus 1 by x. Okay, depending on where you want the image to form. So whether there is a correcting lens or not, magnification is not going to be disturbed. The kind of image you see is going to be different. The orientation of the image you see is going to be different. I should not even say kind of image. The orientation will be different. Is it clear?
Yes, sir.
And another difference this makes is, it changes the length of the telescope. It makes the telescope longer, obviously. And how much longer does it make? It introduces a 2FC and a 2FC in between. So 4FC extra distance will come. Therefore, length of a terrestrial telescope, normally for any telescope, it is, not any telescope, for astronomical telescope, it was f0 plus d. Another 4FC gets added. Okay, so this is the length of a terrestrial telescope. So not a big deal, but see, again, I'm telling you, you won't be able to remember all these formulas for your final exam. You need to know what exactly is being done. So just by visualizing the ray diagram or the way the lenses are placed, the distances, you can tell what is the length of the telescope, you can tell what is the magnification. all those things. Is it clear?
Yes, sir.
Okay, fine. So let's discuss some general questions based on image formation by telescope. Okay, you look at this diagram and tell me. The first image that is formed, okay, first image is formed here, I1. Is it real or virtual?
Real, sir.
Real. Light is actually passing through that image location, so it's a real image. The final image that is formed, I2, is it real or virtual?
They're virtual because
Correct, it's virtual. Yeah, because light is not actually passing through that point, through that image. Okay. And compared to the original object, the final image that you see, is it an inverted image or an upright image? Compared to the
inverted, sir.
inverted image, obviously. Okay. Now see, angular magnification will definitely be greater than 1. It is f0 by fe or f0 into 1 by fe plus 1 by d. Angular 1 by fe plus 1 by x. Okay. Angular magnification is definitely greater than 1, okay, produced by a telescope. That's fine. But suppose they ask you, what is the linear magnification produced by a telescope? Is it greater than 1 or less than 1? What will your answer be? Rishi, what is the meaning of linear magnification?
Sir, isn't that V by U?
See, V by U is a formula. I'm asking you the meaning of linear magnification. It is the height of image divided by the height of object. Okay.
Yes, sir.
Now you have to actually zoom this picture out to understand linear magnification. Yeah, this is what was happening. This is the original object, right? The lens is very small. Let's remove the observer's eye from here. Okay. And where is this? Like if you use another lens somewhere here also, the final image you get is somewhere here, right? It does produce angular magnification. It does subtend a much larger angle on the eye. But the final image is this. Do you think the final image is bigger than the original object?
No, sir.
It won't be. Okay, it won't be. The original object is like a building or something. Okay, or maybe a planet. So final image won't be bigger than the object. But only thing is because it is forming closer, much closer, it subtends a much bigger angle on the eyepiece. Okay. Okay. Fine. That is all you need to know about telescope, length of telescope and all. Good. So next class we will discuss total internal reflection and solve some problems based on it and then move on to prism, refraction by a prism. Okay, fine. Thank you. We'll continue in the next class.